Thank you so much. And thank you all for being here in Kyoto. And I want to start with a few thanks because any award winner does not work alone. And I will acknowledge throughout my talk some of the many people who've helped me. But first I'll begin by thanking the Asahi Glass Foundation, the Blue Planet Prize team, and the AGC Corporation and Chairman Shimomura, who you just heard from. We're grateful for your long-term support of the environment, and thank you for doing that. I'd also like to thank the many years of students and staff and other scientists who've worked in my lab. None of the work that I'll present today would have been possible without their efforts, their ideas, and their commitment to the environment. And finally, I'd like to thank my wife, Sally, who's in the audience, and our son, Will, who's with us here in Japan. They have been a great source of inspiration to me, so thank you again. As you heard, the title of my talk today is Restoring the Atmosphere, Hope, Health, and Humanity. And I'll tell you what I mean by restoring the atmosphere. I'll show you a few examples of that. So let's proceed with that in mind. And let me begin with stating what I think is an obvious fact now, and that is that climate change is here already. This isn't an issue for our grandchildren in some distant generation. It's affecting us here today. What you're looking at here is a trace of temperatures. Each of those bars is a year, and you see that the temperatures for the Earth have gone up over the last 75 years or so steadily. The last 2 years, 2023 was the hottest year on record here until 2024 shattered that record here. 2024 was remarkable for being the first year where the Earth's average temperatures were more than 1.5 degrees Celsius above normal pre-industrial levels. An occurrence I never expected to see in my lifetime, and it's come much more quickly than we expected. So climate change is here now. It's not a distant problem, and we're already paying for climate change today. Billion-dollar weather disasters cost us a lot more money, and our weather's gone weird. I think we all have a sense of this: more droughts, more storms. In the United States, billion-dollar weather disasters occur many times more often today in a year than they did just a couple of decades ago. And they already cost us $100 billion a year that we, as taxpayers, pay for disaster aid and other things. So climate change is here now, and we're already paying for it. And of course, the driving cause for this change in climate is the increase in greenhouse gas emissions and concentrations in the atmosphere. And this is where I'd like to acknowledge hundreds of colleagues in the Global Carbon Project. We in the Global Carbon Project track greenhouse gas emissions of carbon dioxide, methane, nitrous oxide, and other gases. We track them in and out of natural systems, land, forests, the ocean, and then the many things that we do: crops, buildings, oil and gas fields, pipelines, power plants, the built environment. So we put all of these pieces together to try and understand why greenhouse gases are increasing and how to measure them more accurately and reduce their emissions. So that's sort of the core of what we in the Global Carbon Project do. And this is one of our probably best known graphs. Each year we release an annual budget of carbon dioxide emissions for the greenhouse gas CO2 or carbon dioxide. So here you have billions of tons. We now emit about 40 billion tons of CO2 from power plants and burning fossil fuels. And then here are years. And the important message to see here is that we have yet to even stabilize carbon dioxide concentrations, let alone bring them down to zero where they need to be to keep the Earth from warming further. So if you go back to the Kyoto Protocol almost 30 years ago now, fossil carbon dioxide emissions are now more than half, maybe 60% greater than when that agreement was signed here in Kyoto. So we haven't done our job yet to reduce emissions and to begin to bring this problem under control. And that is true for all of the greenhouse gases, methane and nitrous oxide too. They're all still rising. So why are carbon dioxide concentrations rising when we know that our energy sector is changing dramatically, particularly through the use of renewables? So here is a figure, coal, oil, and natural gas for each year. That's how much is used. You see that there's no decrease yet in any single fossil fuel. Over here is the most interesting and exciting bar. The green bars are renewables, things like solar and wind power, and they have risen remarkably quickly, 10 or 11% a year, they're just still a lot smaller than the bars over here for fossil power. And what we haven't done yet is have this renewable power take dirty coal and reduce oil and natural gas offline around the world. We keep consuming more and more energy each year from data centers and many other things. So we add these renewables on, but the fossil emissions and the fossil power plants keep operating because we need that extra energy. So we need to think about ways to reduce energy use. But that's not the only reason that carbon dioxide emissions are still going up. There are sectors of the economy that are hard to decarbonize and that we haven't fully decarbonized yet. This is a picture of a steel plant that I took in Sweden. So this is sort of the old way of producing steel, the same way we've produced steel for well over a century. And in that steel plant, coal is used in a number of ways. It's hard to decarbonize industries that use furnaces where you have to heat things up to thousands of degrees, like in steel production or cement production. It's hard to do that with renewable energy, renewable electricity. And then within these furnaces, the coal that's used provides structure for the gases to move through. So you have to eliminate all of those uses to get rid of coal and make fossil-free steel. But fortunately, that's happening today. This is the same plant. So instead of using the old manufacturing way, they've produced a new way to make steel. And they've replaced all the coal with clean hydrogen that they make on site using clean hydropower. And they use that hydrogen to raise the temperature of the kilns and to provide everything that they need to replace the coal in this operation. So they are now making steel that releases no greenhouse gases. The important thing to remember for this as we think about decarbonizing the whole economy, though, is this would never have happened if countries like Sweden and Finland weren't the first countries to have a price on carbon pollution. It costs these companies about $60 a ton to release carbon dioxide into the air. And by avoiding those emissions, they can spend that money on revamping their manufacturing, to the point that now this new way of making steel, they believe, will be as cheap or even cheaper compared to the old way. So it will win, and they are replacing their manufacturing all around the world, which takes many decades to do. So we need to price pollution. As long as greenhouse gas pollution is free, we will never solve this problem. We also need to think beyond the built environment to think about opportunities and the health of forests and natural ecosystems too. What you're seeing here is a plot that shows the source of greenhouse gases, in this case carbon dioxide, into the atmosphere. Most of that CO2 comes from burning fossil fuels. About 1/10 of it comes from deforestation here. And then here's what happens to that carbon dioxide. Only about half of it stays in the air, and the other half is pulled out of the air by trees and other plants on land, and some of it goes into our oceans. So these are sort of natural sinks, and they for many reasons, they encourage us to take care of our forests and other ecosystems, to restore them, and to recognize the many benefits that those systems provide. Forests don't just take carbon out of the air, they clean our water, they clean the air, they keep soils from eroding, they preserve biodiversity. So there are many, many reasons to preserve our forests, but climate is one of them. And restoring our forests is the cheapest way to remove greenhouse gases from the atmosphere. So it's something that we work on currently in my lab, and I've spent much of my career working on. This is just an example of a project in Scandinavia where we are looking at old growth forests, primary forests, that have never been cut or not been cut for a long time. And they grow in a matrix of industrialized forestry, one species, heavily managed. And so we can study those old growth forests right next to plots that are industrialized and look at how they're different, how much carbon they contain compared to an industrialized site, how different their soils might be and their biodiversity. And that's the focus of this project with a colleague, Kabir Pei, who we study fungal diversity in the soil, the symbionts that partner with plants to remove nutrients from the soil. And my friend in Sweden, Anders Ahlström, too. So let me just show you a few slides on this experiment to give you some idea of the kinds of things that we do. Here's a map of, in this case, Sweden. And these blue and brownish dots are where we've been able to sample these primary forests. You can see some pictures of these forests here. One of our colleagues, Ulrika, enjoying one of the large trees that are found in these systems. So we've sampled hundreds of these plots across Sweden to understand their biomass, how much wood is contained in the trees above ground and also below ground, and also how much soil carbon is there, how healthy the soil is, what the diversity of fungal symbionts and other fungi in the soil are the old growth forests different than these heavily managed industrial forests? Do they contain more species? Is a question that we're looking at. And if they do contain more species, can we restore other forests more quickly by transplanting those mycorrhizal symbionts that are missing in some of these industrial sites? So you see pictures of us here sampling the soil and some of the profiles that we see. Let me show you an example. This is just a video looking down on one of these old growth forests. All I want you to do is to remember this image when I show you a second image in a second of a more heavily industrialized site. If you squint, you can see us working in the center of that image. So this is a healthy old growth forest in Scandinavia. Well, let me take a second and think about what did we find by comparing these older forests to the industrialized ones? Well, the first thing we found is that there's a lot more carbon contained in these old growth forests, and you see that with these two bars here, old growth here, and the industrialized plots here. The light green is the wood carbon above ground, and the old growth forests contain a lot more carbon, about 75% more, but that's really not that surprising because the managed forests are younger and they haven't had time to grow. So that really isn't a shock to us. What was a shock to us was how much healthier the soils were in the old growth forests, and that is shown in the brown bars. So these are the soils from old growth compared to the carbon in the soils from the managed plots. And something about the way we manage forests industrially loses carbon and it makes the soil less healthy in these ecosystems. So why might that be? Well, a couple of hypotheses that we're working on. The first one is that the simple practice of industrial management reduces soil health. What you're looking at here are some planting practices. This row that you see here in that rock, it looks almost like a road, but what that is when the companies take a blade and they cut the soil and disrupt the soil in the rocks to plant the seedlings along that road. And so that disruption of the soil breaks up the organic matter and destroys the soil structure. And you see that very clearly in a second image from above that I'll just show you for a minute here. So this is an industrialized forest system that's been cut recently. In each of those lines that you see is how that soil has been ripped and disrupted, and the soil structure has been destroyed, and the trees are planted along those. So that disruption of the soil lasts for decades while these trees grow. And it results in the organic matter being broken down and the soil health and structure being lost. There's a second hypothesis that we're testing, though, that I referred to earlier, and that is that there's something about heavily managing these soils that results in a loss of the diversity of the symbionts, the fungi that partner with trees to absorb nutrients from the soil. And so this is work of a postdoc, Peter Pelletier, and some other folks here, where we sample the soil. We use molecular tools to extract the DNA from those soil and measure the diversity of the fungal symbionts. And this is work that's in progress. We don't yet have results, but based on what we do have, we see much higher diversity of fungal symbionts, fungal partners in the old growth forest soils. Forests aren't the only ecosystem that I work in or that I'm concerned about. We also work in peatlands and Arctic ecosystems. This is a picture of a peatland restoration project. And we care about the Arctic and peatlands because the Arctic contains thousands of years of plant growth that's fallen to the ground and then frozen. And if that Arctic permafrost thaws, then that carbon becomes available to microbes to be decomposed and enters the atmosphere as either carbon dioxide, which is bad, or methane, which I'll turn to next, which is even worse. So we're concerned about the permafrost because there's nearly as much carbon in permafrost soils as there is in the entire atmosphere. So that's why people sometimes refer to this as sort of the ticking time bomb of permafrost thawing, which is something we can discuss in questions if people wish to. But anyway, I'm going to switch gears to methane because a lot of methane comes out of these permafrost soils when they thaw, or can come out. And methane is rising much more quickly in the atmosphere, even than carbon dioxide. So this is the concentration of methane here, going back from 1980 to 2025. And you see this rapid increase, slight stabilization here. But the last 5 years have seen methane concentrations rise faster than at any time over this instrument record, for reasons that we're still trying to understand now. And one of those reasons, we think, is that it isn't just that industrial activity is increasing, it's that these natural systems are starting to respond to warming and climate change and release more greenhouse gases into our air. That's really damaging because we have no tools, no methods to quench those emissions if and when they start. So this is something we watch carefully in my group and in many groups around the world. So methane is going up faster, and it's a very important greenhouse gas. Here's what I mean by restoring the atmosphere. I referred to this in my title. And what my hope is that for a gas like methane, here's where we are today. Here's where we were for almost 1 million years in the Earth's atmosphere. We want to bring the concentration of these gases back down to this level. And methane is the only greenhouse gas for which this is possible in the lifetime of anyone in this room. It's extremely potent, 80 or 90 times stronger than carbon dioxide, and it's relatively short-lived. It only lasts about a decade in the air. And that means if we could eliminate human-caused emissions of methane, we could see this gas restored, we could see this happen in only about 10 or 20 years. Doing that would save us 0.5 degree C of warming and would save hundreds of thousands of lives because methane in the atmosphere leads to increased surface ozone, the bad ozone that kills hundreds of thousands of people. So by restoring the atmosphere, we'll help climate and make ourselves healthier. So in the Global Carbon Project, we track methane and other greenhouse gases, where they come from in different geographies, where they come from in different industries. And here's a plot that my colleague Marielle Sonnois in France led. Each of these arrows is a source of methane to the atmosphere, or something that destroys methane on the right. So here's the energy emission from mining and extracting oil and gas and coal and methane leakage. That's about 100 million tons a year. Agriculture is actually the biggest human-caused source. It's mostly cows, rice farming, and some waste material in landfills and other things. So these are the two industries that we focus most of our attention on to try and reduce emissions today. But here's the largest natural source. These are wetlands around the world, and they are large, and we also think there's evidence that natural emissions from wetlands are increasing. And I'll show you a few examples now. Tropical wetlands are where I work currently because they are the largest natural source of methane today. They emit more methane per hectare and emit more methane overall than any other place on Earth. They're warm, they're moist, they're sort of perfect habitats for microbes to chew away at carbon in low oxygen environments and release that carbon as methane to the air. That's just a picture in the Amazon. Here's a photo on the right of a new monitoring tower that we just established with colleagues at the Mamiroa Sustainable Development Reserve. So we're monitoring carbon dioxide and methane emissions up and down this tower to understand how much is coming out of the forest and going in as well, so what that balance is. A really nice thing about doing the job that people like Jeremy and I have is that we get to work in beautiful natural systems, and while I'm there, I see and take pictures of jaguars and giant river otters. It's a beautiful place to go, so it's a source of enjoyment as well as a place to work. And here's just showing where we're doing this. This graph shows you where around the Earth there are monitoring towers for methane. The ones that are in blue currently exist. The ones that are in red are the ones that we are establishing. And what I want you to see here is how little we know about the tropics and how little time and money we spend monitoring in tropical ecosystems. And that's the gap, one of the gaps that we're trying to fill on this project. These are colleagues establishing chambers, putting chambers on trees, measuring them. And down at the bottom, most importantly, are the people really doing this work, my colleagues in Peru, French Guiana, Brazil, Botswana, who run these towers and are local experts. So as I said in the beginning, no one does anything alone in this business. We're focused on the Amazon because the Amazon is vulnerable. Last year and 2023 saw the worst drought in the Amazon that we had ever seen in more than 100 years of record keeping. The river levels of the Amazon were the lowest in a century. Water temperatures were unbelievably high. Water temperatures in parts of the Amazon topped 40 degrees Celsius. And as a result of those temperatures, river dolphins literally died from heat shock. They could not survive these temperatures and just washed up onto the shore. And because of the drought that drove some of those extreme temperatures, the Amazon saw 20 million hectares burned in 2024. Just last year, that's about the size of my home state of California. So huge swaths of the Amazon burned in places that didn't typically burn in previous years. So there's a lot of reason to worry about what's happening in nature. The things that we're doing through industrial activity don't just stay in our cities and in the built environment. They're moving into nature and changing how these ecosystems work. So let's talk a little bit about what we can do about this. Much of the current focus in my lab is on reducing energy-based emissions in the built environment. We fly helicopters to film oil and gas wells to find leaks. We put sensors on top of skyscrapers like this tower in Boston to understand the metabolism of cities and how much pollution is being released there. We drive cars around cities to measure leaky pipelines and try and get them fixed. And then we also work in homes and buildings to try and understand what's coming out of the appliances and the infrastructure that we use in our homes and buildings when we spend 90% of our time indoors these days. So I'll give you a few examples and we'll finish. Here's a video. You're up in a helicopter now and you're looking down on an oil and gas well. This is in Texas. Those are tanks. That's an oil and gas well. That plume that you see is invisible to the naked eye. You have to have a special camera to see that. You see a house up here and a road here. So if you drove along that road, you wouldn't see this. Or if you lived in that house, if that wind changed direction, that plume would blow across the people living in that home and they would be breathing that air. So we visited 10,000 sites like this randomly across the United States. I refer to these as restaurant inspections. You know, the inspectors show up at restaurants. They don't have to get permission to do that. You just show up from the air, you film, and then we try to understand why these leaks occur and who owns these facilities and work with regulators and the companies to try and get them fixed. So this is the old way of doing this. The new way is to do it from the sky, and there are many satellites launching now that are able to peer down on the Earth and find large leaks from space. This is a really tremendous advancement in our ability to monitor emissions. Carbon Mapper is a new satellite that is like a zoom camera. It's in space, but it can zoom in on site-by-site emissions and find plumes. This is an oil and gas facility in Texas. This is a landfill in Pakistan, and here's the source, and the wind is blowing that pollution this way, and here it's blowing down this way. Super emitters like this are important because less than 1 in 100 of facilities releases half of the pollution from these sites overall. So put differently, if you could find the bad actors, the 1% of facilities that are doing this, you could cut half of greenhouse gas emissions from these sites. So that's what satellites like Carbon Mapper are trying to do. Another beautiful thing about this is you don't need permission to fly an airplane. You can't get permission to fly an airplane in Russia or China or Azerbaijan, but from space, there's nowhere to hide, including in the United States. You know, the satellites just look and find all of these in real time. So I'm really excited about these advances. But we can't do everything from space. We also have to take measurements from the ground, in this case from cars or with cameras. This is a city map. With my colleague Nathan Phillips, we produced the first maps of natural gas leaks across cities. So this city is Boston, You can imagine a car that has a new methane analyzer in back and a GPS unit, and you drive the city like a lawnmower up and down every block, every street, back and forth. That's what you see in red. And every one of those yellow spikes on this map is a pipeline leak that emits methane, natural gas, to the air. So we mapped more than 3,000 leaks across Boston, mostly because Boston is an older city and it has old cast iron piping that in some cases date back for 100 years. And so we don't replace infrastructure very quickly, and that's unfortunate. But sometimes the power of science is that it can catalyze work that many people have done over many years and even decades. And that was true for this study. The day we published our paper and produced that map for Boston, the mayor of Boston, Tom Menino, commented on it. The congressperson, Ed Markey, now in the Senate, wrote a letter to the federal agency responsible for pipeline safety. And both of them called for greater scrutiny on the source of emissions, not just for climate, but for safety. Each one of those leaks is a possible place of explosion. So it was really safety that catalyzed this response more than climate. And then the good thing was the next year, the state of Massachusetts passed a law to accelerate repair and replacement of these pipelines as a result of this map. The same thing happened in Washington, D.C. The following year. We mapped 6,000 leaks there. This is the Capitol Hill, the Congress building. Here's all the methane spikes behind it, you see. And here's the city of Washington, D.C. Each of those dots is a leak. And the Public Utilities Commission here, too, passed a new accelerated repair mandate that they estimated would improve the safety and reliability of the system for 165,000 customers of theirs. So these changes are happening. They're just happening too slowly, and we need faster ways to detect these leaks and faster ways to act upon them. Let me end with what can we do at home? What can we do individually? So to reduce methane emissions individually, we can start by replacing fossil natural gas and fossil fuels with cleaner electricity in our homes and in our lives. We can alter our diets. The largest source of methane to the air is food, particularly beef. We can eat a more vegetarian or more plant-based diet. We can waste less food because organic matter that ends up in landfills goes to the atmosphere often as methane. So by changing our diets and selecting clean energy, as you'll hear from Jeremy shortly, we can make a difference to this problem. There's another reason to replace the natural gas in your appliances. Here's a student looking at a gas stove and a pot here. You would never stand over the tailpipe of a car breathing in that pollution willingly, and yet we stand over a gas stove and breathe the same pollution into our lungs day after day, meal after meal. And our stoves don't have a catalytic converter the way the cars do. So one of the things I work on currently is to understand those indoor pollution sources and to try and get them fixed, particularly for people in lower income communities who don't have the money to replace their appliances very easily. So I'll finish with a few examples of that. First of all, the indoor pollution that comes from cooking, it's not primarily from your food, it's from the fuel. Or as I like to say, it's the flame, not the food. Here are two plots. This is a carcinogen, benzene here, and a NOx here is an asthma trigger that triggers asthma in our children and the elderly. So here are the two fossil sources, both substantial. And electric you see here, just none of that pollution whatsoever. So by eliminating or replacing fossil with electric, we eliminate a large source of carcinogens, asthma triggers, and other disease-causing gases in our air. So you can reduce the risk through ventilation, but you can't eliminate it. The best thing we can do is just to eliminate the pollution entirely. Just a couple of traces. Each of these lines is a house where we measured. This is NOx or nitrogen dioxide here, and hours, a time here. The black line that you see here is the Environmental Protection Agency's recommendation that outdoors we should not let NOx go above that level. All right, so in 3 of these 6 houses, indoors, as soon as the family turned their stove on, the concentration of NOx rose well above this threshold of safety and stayed there for hours after that appliance was turned off. This isn't the kitchen, this is the bedroom down the hall. So one of the things that we do now is to work with community groups, asthma collaboratives, groups trying to replace infrastructure in lower income homes like Sustento and our partners Esperanza. We just worked with them to electrify a building with 30 units in Los Angeles. They replaced the gas stoves with electric, and we monitored that transition with our instruments. And I'll show you an example of what we found next, and we'll finish up. So here's one apartment unit where we had our monitors in the kitchen, living room, and bedroom. The first week is when the gas stove was present in the home. The second week is when they had replaced that gas stove with an electric induction unit. These concentrations are what people are seeing in the way they live normally, day to day. This is just a family cooking normally for their kids, using their hoods, opening windows as they do, and you see these concentrations rising above this threshold regularly. And when the induction stove is placed into the unit, that threat disappears entirely. So climate action isn't just about improving our climate, it's about our health today, and that's the message that I would like to leave you with, and why I'm donating my Blue Planet Prize funds to Stanford to create a new electrification for health program. And Stanford is generously matching those funds. So we'll use this money to work in lower income communities and try and get more of them, more help for people in these communities. So I'm grateful once again for the Blue Planet Prize money. So I'll finish just by saying we know that fossil fuels are bad for climate, but we forget that they're deadly, even in spite of the progress that we've made in air quality around the world. Fossil fuels are still responsible for 1 in 5 deaths worldwide today, primarily from particulate pollution. That's 10 million people every year who die around the world unnecessarily when cleaner energy is available today. So in many sense, we can think about climate solutions, not just about climate, but because they promote jobs and national security and health. There are many reasons to promote clean energy, and we have to be mindful of that as we try and build a coalition for climate solutions and clean energy. And I'll just say that, as I said, climate action will make us healthier. When I work with students, I try and remind them that there are many things today that are better than they were when I was a boy. Our water and air quality around the world is generally better. People live longer. Childhood mortality is lower. Global poverty has declined despite the injustices that remain. But there are also specific things we've done through environmental regulations that are saving lives and money as well. Japan was the first country to ban lead in the gasoline of automobiles. And now every country in the world has done that over the last couple of decades. Banning leaded gasoline has saved $2 trillion a year, continues to save $2 trillion a year, and has literally made us smarter because lead reduces brain development in our children. So millions of our kids were damaged by the lead in the environment around them, and that has essentially gone away. Blood levels are now 96% lower than they used to be prior to this ban. So this is a success story that people have got together, done the right thing, and made us healthier. Montreal Protocol is the greatest environmental agreement to protect the ozone shield. It's done the same thing, saved lives, skin cancers, cataracts. My personal favorite is the Clean Air Act in the United States. This was always a bipartisan bill, Republicans and Democrats. It saves over 100,000 lives a year at a 30-fold return on investment. So for every dollar that we spend cleaning up the air, we save $30 because our workers are healthier, we spend less time in the hospital, and everyone benefits. So I introduced this idea. This is my dream as a scientist, to see the atmosphere restored for methane, to bring it down from current levels to these, to save warming, to save lives. And it's that intersection of clean energy, climate solutions, and health that I'd like to leave you with today. So thank you for listening, and I'm grateful for you being here, and to the Blue Planet Prize again.